Hello everyone, welcome to this HEMI 2010 final review. And for the final review, I have already posted the practice final exam answers on your Carmen page for HEMI 2010. But what I want to do is I want to spend some time solving a couple of the problems from there. And my choice is to solve two problems from your practice final exam. One of them is on frames, the other is on friction. Okay, so let us start with the problem on frames. Okay, so here is the problem. I'm just going to pull out the figure from your practice final exams. Okay, so here is the figure, and you are told that in this frame there is the bar ABC, then there's the bar CD, there's the bar DEF or FED, and then there's the bar BE, and we need to find the support reactions in the pins A, B, C, D, E, and F. Okay, all right, so here is the problem. Okay, so problem. Okay, we need to find the reactions at pins A, B, C, D, E, and F. Okay, and furthermore, if you look at the problem statement in your practice final exam, it tells you a couple of things. It asks you to start drawing the free body diagram of the entire frame. Okay, so draw the free body diagram of the entire frame. Okay, and then it is also asking you to draw the free body diagram of the individual bars of the frame. Okay, so draw the free body diagram of the bar ABC, then the bar CD, then the bar DEF or FED, and then the bar BE. Okay, these are the two things that you're supposed to be drawing. Okay, and let's start off by taking a close look at this problem. First of all, the basic idea is if I see distributed forces, I have to get rid of them. Okay, so that's the first thing I'm going to do. If I look at this 150 pound per foot force, it's acting over a span of 5 plus 2, 7 feet. And my first thought process is to get rid of that by drawing a resultant force FR1. Okay, so I'm just going to draw that on this figure itself so that it's obvious to us as to what to do. Okay, so in this problem, I'm going to say that, okay, here is a force FR1. Okay, so I'm just going to call it as FR1. Then I'm going to have a force FR2, which is sitting right there. Okay, so that force is FR2, and then I'm going to have a force FR3, which is acting right there. Okay, so this is going to be the force FR3, and it's quite obvious to see that the force FR1 is going to be the area under the distributed loading, which is 150 times 5 plus 2, 7 feet. So this is going to be 150 times 7, or 1050 pounds. Then the force FR2 is going to be the area under the triangle, so that's 150 times 4 by 2, or 300 pounds. Okay, so this is going to be half times 150 times 4, or 300 pounds. And then FR3 is going to be 150 times 2, which is the area of the rectangle, right? 150 times 2, and that's going to be 300 pounds. Okay, so this is the first step in most of these problems. I'm sorry, I had to draw a curly bracket here. Okay, so the first step is to get rid of the distributed loading. Okay, so that's the first key step. Okay, so reduce the distributed loading to equivalent resultant forces, or replace the distributed loading by single equivalent forces. Okay, and it's fairly straightforward. You've done enough problems now to see that if you have a rectangular loading, then this is going to be acting at a distance of half the length of the rectangle. So that's going to be half of 5 plus 2, 7 feet. So this is going to be at a length of 3.5 feet from the point A. Okay, that's also something that you can quite easily see. Okay, so that's something I can mark off here. Okay, this is going to be 3.5 feet from the point A, right? And then if I look at this triangular loading, it's going to be at a distance of 2L by 3 from the pointed end, or L by 3 from the bigger end. So that's 2 times 4 by 3 from the top end, and that's going to be about 2.67 feet. Okay, so if I look at that, this length here is going to be 2.67 feet. Okay, these are all things that we've seen before, so I'm not going to spend too much time on that. And then likewise, you see that this is over a distance of 2 feet, rectangular loading, so its FR3 is acting at a distance of 1 foot from the point F. Okay, so if I mark the distance here, this is going to be 1 feet. All right, so that's the first thing that we did. We took the distributed loading, replaced it by single equivalent forces. We found out where they act, and so my next step is to draw the free body diagram of the entire frame. Okay, so let me start off by doing that, and I'll look at different colors for the different bars of the frame. And I've already reduced the forces into FR1, FR2, and FR3, and I know the distances where they're acting from, so I'm going to just make use of that information. Okay, so probably I'm just going to copy this information. Okay, and bring it down so that I can draw the free body diagram of the entire frame. Okay, so here is the situation that I have, and perhaps I can reduce it by a small amount. I guess not. Let me just stick with that then. Okay, so this is the situation that I have, and let me start off by looking at the free body diagram of the entire thing. Okay, so I have the bar ABD, which is drawn in the following manner. Okay, so here is let me do that using these colors here. Okay, slightly thicker ones. So this is the bar ABD. Then I have the bar CD, which I'm going to draw using a different color. Okay, here's the bar CD. Then I have another bar, which is FED, starting from here all the way down to there. Okay, that's the bar FED. And then in the intermediate step, I have this bar here. Okay, all right. And here are the things that are happening. These are all pinned together. These are also pinned together. You'll see that in this particular problem on the frames, there are only 2 members of the frames connected at each individual pin as such. So I don't need a pin free body diagram, but I still need the free body diagram of the support reaction. So at A, I have AX and AY. So I'm just going to draw them as AX here. Okay, and then I'm going to have AY. Let me assume it to be pointing vertically down. Okay, so this is AY, and then at this point I'm going to have FX and FY. Okay, so this is going to be FX, and then here is the force FY. Okay, and then I'm going to have the resultant forces FR1, FR2, and FR3 as we have drawn here. Okay, so these are the forces FR1, which I'm going to be drawing right down here. Okay, so this is FR1. Then I'm going to have the force FR2, which is acting on this bar CD, and then I'm going to have the force FR3, which is acting right there. Okay, so this is going to be FR1, which is 1050 pounds from before. Okay, this is FR2, which is 300 pounds, and then this is the force FR3, which is also 300 pounds. Okay, these are the equivalent forces, and then we need to have the distances as such. We will be marking distances by the dotted lines. So let me do that here. Okay, so the first distance here is going to be a distance of 3.5 feet. Okay, so this is going to be 3.5 feet, and then I'm just going to mark these distances here as well. Okay, just so that we know what we're doing. Okay, this is 1.5 foot. Okay, as you can see, net from FR1 to the point B is 5 minus 3.5, so 1.5, and then I have 2 feet here. Okay, so this is going to be 2 feet, as you can see from the figure. Okay, and then this length here is going to be 2.67. Okay, so this is 2.67 feet. and then this distance here, the remainder of the distance is going to be 1.33. So if I can mark that out here, let me draw that here. Okay, so this is going to be 1.33 feet. Okay, and then these distances are known to us. This is a distance of 1 foot, and then the remainder of the distance, that's 5 plus 1, that is 6 feet. Okay, so starting from here to there, which is also 1 foot. These distances are all needed for us because we are going to draw the free body diagram of the individual bars as such. Okay, and then this distance also is given to us in the problem, and that's 5 feet. All right, so this is the entire free body diagram of the frame. Okay, from this we can immediately see that there are 4 unknowns. There is ax, ay, there is fx, fy, which means that in the best possible scenario I can find only 2 of the unknowns. Okay, so I just want to make a note of that. Okay, so there are 4 unknowns from the free body diagram of the entire frame. That's ax, ay, fx and fy, right? So at best we can find only 2 of these. So at best we can find only 2 of the above unknowns by looking at the free body diagram of the entire frame. Okay, by looking at the free body diagram of the entire frame. Okay, let me write that as entire frame. But something is better than nothing, so I'm still going to be taking a look at that. What I'm going to do is I'm going to sum forces in the x and the y directions, and then some moments about a certain point. Okay, if I sum forces in the x and the y directions, I find out that ax and fx are related to each other. That's going to be ax plus fx is equal to 300 pounds, which is fr2. Okay, so let me do that first. Okay, so sum of forces. So maybe I should just copy this figure down and bring it down to the next page. So let me do that. Okay, I appreciate your patience with me on this one last time. So I'm going to bring that guy and I'm going to paste it here. Okay, and I'm going to start summing forces up. Okay, so sum of forces in the x direction, I'm going to set all the forces in the positive x direction to be positive. So this is going to give me ax plus fx is equal to 300, right? That's quite easy to see. So that's one thing that I can do. The second thing I can do is I can sum forces in the y direction and set that equal to 0. What are the forces in the y direction? I have 1050 and then I have 300. So ay and fy are related in the following manner. So this is fy plus 300 minus ay minus 1050 is 0, or fy is going to be ay plus 750. Okay, I just want to put a box on these things. So here is one situation. Let me duplicate that. Okay, and I'll be bringing this creature again towards the end of the problem. I'm just going to write this as ay properly. Okay, so this is ay plus 750, and then the last thing that I can do in this frame, I have only 3 equations, and one thing I've seen people do is apply the moment equations again and again on a free body diagram. No matter how many times you use the moment equation, you are still going to get only one equation. Okay, you can apply the moment at millions of points on the free body diagram or outside the free body diagram. That doesn't mean that you end up with millions of equations, right? I have only 3 equations of static equilibrium for a 2-dimensional problem. I have sum of forces in the x direction, sum of forces in the y direction, sum of moments at any arbitrary point on the body or outside the body. It does not matter where it is. The key thing is it's an arbitrary point. Okay, so if I apply this at different points, it doesn't mean I end up getting different equations and I can solve for the unknowns. If you are stuck, you are stuck. There is no way you can undo the damage. Okay, so when you're applying the moment equation, you are going to get only one particular equation which is of use to you. Okay, All right, so the third step is to apply the moment equation. I'm going to do the moment balance at the point A. Okay, so I'm going to say, okay, sum of moments at A is equal to 0. And I'm going to say that, counterclockwise moments are positive. So just going to scoot this creature up a little bit. Okay, counterclockwise moments are positive. So what are the moments? I have fx times a distance of 4 feet. Okay, so this is going to give me fx times 4. Then I'm going to have 300 times 1, 300 times the fr3, the force fr3. Then I'm going to have minus 1050 times 3.5. And then I'm going to have minus 300 times 2.67. This is equal to 0, which means that I can solve for fx. Okay, so fx, if I solve for fx, is going to give me 1044 pounds. Okay, so this is the answer I get for fx. All right, and once I have fx, then I can find out one of the other unknowns, which is ax, because I have a relationship between fx and ax. Okay, so I have found out this guy, which eventually tells me that ax, which is 300 minus fx, which means ax, according to the direction that I've chosen, is minus 744 pounds. Okay, so these are the equations that I have obtained by looking at the free body diagram of the entire frame. Not very useful, but at least somewhat useful. Not a terrible thing. Okay, so I have at least found out two of the unknowns. I have a relationship between the other two unknowns. Okay, so which means that to proceed further with the problem, I have to completely dismantle the frame. Okay, so to proceed further, okay, we dismantle the entire frame. Okay, and then we draw the free body diagram of the individual bars of the frame. Okay, so which means that we draw the free body diagram of the individual bars of the frame. And we also notice that at the pins, if you call this as pin B, this is C, this is D, this is E, and then F. So at pins B, C, D, and E, there are only two members of the frame connected to each other, which means the forces at those two members that are connected are equal and opposite, so I don't need to draw the free body diagram at those pins. Okay, so that's also something that I want to make a note of. Okay, so notice that at pins B, C, D, and E, only two members of the frame are connected together, which means that we do not need a pin diagram at these two pins, at these 4 pins. Okay, so we do not need to draw a pin diagram at these pins. Okay, and the key statement is if you have more than two members connected at a pin, then you need to draw the pin free body diagram. Okay, if you have more than two members of a frame connected at a pin, then we need to draw the pin free body diagram. Okay, the key statement being that if you have more than two members connected together at a pin, okay, more than two members of a frame connected at a pin, then you need to draw the pin free body diagram. In this case, we don't need it because there are only two members of the frame are connected together at those pins, so we do not need to draw the pin diagram at these pins. Okay, all right, So our next step is to take a look at these different bars, and then we will start looking at what information we can glean from them. And I'm just going to inspect and see if I have enough space. I don't have, so I'm going to start drawing the free body diagrams on the next page. So far what we have is from the free body diagram of the entire frame we have the following. Okay, so from the free body diagram of the entire frame we have the following. Okay, I'm just going to copy these results so that I can capture them when I need it. Okay, so just going to copy that and paste them here. Okay, right, so that's one, then that's another, that's nothing, and then the third thing, which is the relationship between Fi and Ay. Okay, so that's a fairly important thing as well. I can perhaps make use of that when I need it. Okay, and so the next step is to draw the free body diagram of the elements of the frame. Okay, so next step, draw the free body diagram of the elements of the frame, elements or members of the frame. Okay, so let's start off by looking at that. So we had, let me copy this figure so that I can take a look at it, or let me not copy it, let me just inspect the figure. So I have the bar A, B, C, the bar C, D, the bar F, E, D, and the bar E, B. Okay, so let me start off by drawing those free body diagrams. Okay, so here is the bar A, B, C. Okay, so bar A, B, C, if I can draw it right down here. Okay, then I'm going to have the bar CD. Okay, I'm just going to scoot that down and draw it right here. Okay, so this is the bar CD. Okay, then I'm going to have the bar DEF, which I had drawn in this particular color, I think. Okay, so that was the bar DEF, and let me make sure that this is the same length as that guy. Okay, and then I had the bar BE, okay, or EB, which was drawn in the following manner. So let me just draw that bar here. Okay, and let's start labeling the points. So this was point B, this was point E. Okay, this was point C, and then this was point D. Right, so this was the point D, then this was the point F, and then likewise this was the point E. Okay, and here was the point A, and then here was the point B. Okay, and then this was the point C. Okay, so let's start off by drawing all these forces, and we see that okay, at the pins B, C, D, and E, the forces acting are equal and opposite. I'm going to assume, look at the bar BE, this is a two-force member, right? The bar BE does not have any other forces acting on it except at points B and E, so this is a two-force member or a two-force bar, so this is a two-force member. Okay, which means that for the bar BE, I'm going to assume this to be in a state of compression, so I'm going to have force FBE, which I'm going to draw this way. Okay, so this is the force FBE, and then here is the force FBE as well, of course along the line joining the points B and E. Okay, so this is the force FBE, sorry. Okay, and so I'm just going to label this as FBE. This is also FBE. I have a nice slope triangle for the bar BE, which is 3, 4, and 5. If you go back to the figure and see the values of the different distances, you'll find out that this is a 4, 3, 5, and 5 slope triangle. Okay, I just want to make sure that I have enough space to draw these things, so I'm going to take this bar and scoot it up a little bit, okay, so that I have it here. This is the bar FBE. Now at the point A, I had the support reactions which we had calculated earlier, one of them at least. That's going to be the force AX. Okay, then I had the force AY, which was acting vertically down. I do not change its directions. I'm just going to maintain the same directions as I had before. Then at pin C, I'm just going to assume CX and CY in the following directions. Okay, so I'm going to assume CX to be pointing this way, and then CY to be pointing the other way. Okay, pointing vertically up. Okay, this is going to be CY, and this is the point C. If I write it down here, so this is point C, and at point B, I'm going to have a force that is equal and opposite FBE, which means that this is going to be pointing in the direction opposite to that. So I'm just going to copy that and bring that guy down here, and then I'm going to say, okay, this is going to be FBE for me. And of course, on the bar AB, I also had this distributed force FR1, which was acting vertically down, as you remember from before. Okay, this was equal to 1050 pounds. Okay, so this is FR1, which is 1050 pounds. And then we had distances. Distance from A to B was known to us as 3.5 feet. Distance from point where the FR1 is acting to the point B. Let me scoot this down and write this here. So this is the point B. Okay, and this distance was 1.5 feet, and then the remainder of the distance was 2 feet. Okay, then I come back to the pin at C. If I had CX and CY drawn in the following manner on ABC, then I have to have equal and opposite forces, which means that I'm going to have the force CY pointing down and CX pointing to the left. So let me take this point and then write it down here, so that I have the force CX pointing this way, and then the force CY, which is pointing this way. Okay, then I had the equivalent resultant force FR2, which was acting in the following manner, right? If you recall, this was FR2 was equal to 300 pounds. And then I also have the pin at D, where I can choose the direction of dx and dy, and I'm going to choose the direction of dx and dy as the following. Okay, so I'm going to say this is the direction of dx here, and then I'm going to say dy is pointing vertically up. Okay, who says this? I say this because I can choose the directions on one of the pins, but then on the other it's going to be equal and opposite to that. Okay, I just have to get rid of this guy. Okay, so this is going to be the pin at D. I'm sorry, I'm just going to call that as D here. And then I have distances from C to where the force is acting is 2.67 feet, and the remainder of the distance is 1.33 feet. And then lastly, I have this bar FED. I'm just going to scoot this down a little bit so that we have enough space to draw it out. Okay, so here is the bar FED. And if you look at the forces, first of all, at the pin at F, I had forces Fx and Fy. Okay, if you recall, this was the force Fx, and this was the force Fy. Right? This was force Fy, and then at pin E, I'm going to have FBE, which is going to be equal and opposite to whatever I had here. Okay, so if I just duplicate that and bring that here, okay, so that's going to be FBE, and I have the slope triangle which is given to me, which means that at the pin at E, I can break FBE into its components. Okay, so I'm just going to break it into its components, which is going to be one of them which is going to be acting vertically down. Okay, and the other one which is going to be acting in the following manner. Okay, and the slope triangle is 4, 3 and 5, as you can see. So if I maybe scoot this guy and bring it here, and perhaps extend the length of this guy, okay, you can see that this slope triangle is 4, 3 and 5. Okay, so this is 4, this is 3, and then this is 5, which means that this is going to be 4/5 FBE, and this is going to be 3/5 FBE. Okay, and then at the pin at D, I'm going to have equal and opposite dx and dy. So let me draw that out and then mark the pin at D. So this is going to be dx pointing to the left, and dy, which is pointing vertically down. Okay, so this is going to be dy, this is going to be dx, and then this is the pin at D. Okay, and then this is the pin at E. I'm sorry. And then I have distances, and I have one more force, FR3. I'm sorry, which is acting as shown here. So this force was equal to a value of 300 pounds. FR3 was 300 pounds, and then we had the distances. This was 1 foot, this was 1 foot, and then the distance from E to D was 5 feet. All right, and so we have the free body diagram of all of these. Okay, we have the free body diagram of A, B, C. Then I have the free body diagram of F, B, E, which is a two force member. So I'm just going to scoot that and have that stand alone by itself. Okay, so this is the free body diagram of FBE, and then I have the free body diagram of CD, and then free body diagram of FED. And then my choice is, I can start off with any one of these free body diagrams. I'm going to start off with the easiest of the lot, which is this vertical bar CDE. Okay, so I'm going to start off by taking the free body diagram of the bar CD and trying to find as much as I can. Okay, so look at free body diagram of CD first. So look at FBD of the bar CD. Okay, if I look at the free body diagram of the bar CD, here is what I'll find out. Okay, if I sum the moments at the point D, okay, so if I start summing moments at the point D and setting all of them equal to 0, here is what I end up getting. So I'm going to see that CX times the distance of 4 feet. Okay, then I'm going to have FR 2 times the distance of 1.33. That's going to be positive as well. So plus 300 times 1.33, this is equal to 0. Or if I solve for CX is approximately minus 100 pounds. Okay, so this is what I end up getting. And of course, you'll see that there are 4 unknowns in this free body diagram as well, which means that the best case is that I can find out 2 of the unknowns and I can find an equation for the third one. Okay, then I can say that sum of forces in the x direction is equal to 0. If I set that equal to 0, then I can find out dx plus cx minus fr2 is equal to 0, which means that if I solve for dx, that's going to be 300 minus 100, so approximately 200 pounds. I'm sorry, this is minus cx, I apologize. This is dx minus cx. Okay, and so I see that dx is going to be equal to 200 pounds. Okay, so once again I can duplicate this and put a box around this particular answer here. Okay, then one more equation that I can obtain, I guess I'm going to draw this in the red color. One more equation that I can obtain is the relationship between dy and cy by summing forces in the y direction. So if I sum forces in the y direction and set them equal to 0, what I end up getting is dy is equal to cy. Okay, and I guess I should be copying that and pasting that here. Okay, and that's the last thing that I can obtain from this free body diagram. There is no more information that is useful for me in this free body diagram, and I want to scoot this so that we don't have this going to the next page. So this is the situation. So we are done with the free body diagram of CD. Maximum information that we can has been obtained. Now the choice is, I can look at the other 2 free body diagrams. What are the other things left? I'm already done with the free body diagram of BE. I found out that this is the this is a 2 force member. So we are done with the free body diagram of BE. This has done its job. Okay, so this is done. The free body diagram of this is done. I can either look at ABC or I can look at FED. So let me look at FED. Either one of them is easy. Okay, if I look at FED, so I'm just going to copy this and I'm going to bring it to the next page and say I'm going to look at the free body diagram of the bar FED or ABC. Okay, so I'm going to look at to analyze FED. This is not FBD, this is FED. I'm sorry, this is FBD of FED. I'm going to look at the bar FED. Alright, and here is its free body diagram if you draw it out. And there are things that we know. dx we found out to be 200 pounds. Okay, so I'm just going to write this as equal to 200 pounds. Then we also had information on Fx. If you remember, Fx was equal to 1044 pounds. Okay, so this was 1044 pounds from above, from some calculations that we did on the free body diagram of the entire bar, which means that my first step is to start by looking at sum of forces in the x direction, because FBE is the only unknown. Okay, so which means if I sum forces in the x direction and set that equal to 0, I'm going to have Fx minus 3/5 FBE minus dx is equal to 0. Okay, which will give me FBE. If I solve for FBE, I get 1407 pounds, approximately. 1407 pounds. Okay, so if I put a box around this answer, because this is a crucial piece of information, we're almost done. Okay, with this particular problem, you see, it is not that bad. If you have a basic strategy for solving these problems, it is not such a bad thing. So the first thing I would do when I look at a frame problem is strategize, see what you're going to do. Okay, then you start taking it step by step. Okay, so FBE is obtained. Then I can sum moments about the point F. Okay, so let me do that as the next step. Okay, sum of moments about the point F is equal to 0. So if I sum those moments up, here is what I end up getting. Okay, so I have FR times 1, FR3 times 1, then I have 4/5 FB times 2, negative. Then I'm going to have dy times 5 plus 2, 7. Okay, so that's minus dy times 7. That's equal to 0. Well, I guess I also have to right, this is all I end up having. Okay, that's equal to 0, and I have to solve for dy. Dy is the unknown here. Okay, so which means that if I solve for dy, I end up with a negative answer because FBE is slightly larger than FR3, right? So this is going to be minus 278.7 pounds. Okay, and I'll put a box around this. Okay, and we had also, I guess I just want to point this out after putting the box around here. Okay, from the free body diagram of the bar CD, you had found out, that dy is the same as cy, right? So I'll bring this equation here. Okay, I'm just going to copy it. Okay, so from the FBD of CD of bar CD, we had this guy, right, which tells you that cy is also equal to minus 278.7 pounds. Okay, I'm just going to copy that and put a box around this creature as well. Okay, whenever possible, if you box your answers, that's easier for me when I'm doing the grading. So I'm trying to follow the same procedure here as well. I guess I should have this in the red color. Okay, so this is the value of cy, and then the last thing that I can do for the bar FED is I can sum forces in the y direction. Fy is an unknown. If I know Fy, then I can find Ay, and then I'm done with this problem. Okay, so if I sum forces in the y direction, I get the following. Okay, so on the same bar, okay, on bar FED, okay, I sum forces in the y direction and set them equal to 0. What are my forces? I have Fy going up, FR3 going up, dy going down, 4/5 FB going down. Okay, so I'm going to have Fy plus FR3 4/5 FBE minus dy is equal to 0, which means I solve for Fy and I end up getting 546.6 pounds. Okay, put a box around this creature as well, and the very last step that we have, as you might recall, is we had obtained a relationship between Fy and Ay by looking at the free body diagram of the entire frame. Okay, so from the free body diagram of entire frame, we had the following equation between Fy and Ay. I'm just going to bring that creature down here. Okay, so that is this guy, and if I bring that here, so this is what we had, which essentially tells me that Ay is going to be Fy minus 750, or this is minus 203.3 pounds. Okay, so minus 203.4 pounds. If I want to put a box around that creature, okay, and we are almost done with this particular problem from that perspective. Okay, so I have found out the forces in all of these bars as asked by the problem. Okay, so if I go back to the problem, a very quick summary is the following. I'm just going to go look at the main figure of the problem. First step is I was given distributed loading, so I replaced the distributed loading by single equivalent forces. Okay, this was the first step. Okay, you can see that rectangular loading is area under the rectangle, triangular loading is area under the triangle. Where does the triangular force act? It acts at the centroid of the triangle, which is at a distance of 2L by 3. Okay, so this is at a distance of 2L by 3, and this is at a distance of L by 2. Okay, L by 2 meaning this is 7 by 2 or 3.5 feet. This is 2 times 4 by 3 or 2.67 feet. Once I do that, then I draw the free body diagram of the entire frame. This is because the problem is telling me to do that. Even if that is not the case, I would inspect and see. Even if I have 4 unknowns, if I draw the free body diagram of the entire frame, I'm still capable of obtaining 2 of the unknowns. I might not end up getting all of them, but it is still a useful exercise. So I draw the free body diagram of the entire frame. I have 4 unknowns, and at best I can find 2 of them, and that's essentially what we do. We sum forces, we sum moments, and we find out Ax and Fx. We have a relationship between 2 of the other unknowns, which I can make use of later. And then my next step is to take this free body diagram and completely dismantle it. Okay, if I do the dismantling, I have the bar ABC, I have the bar BE, I have the bar CD, then I have the bar FED. BE is a 2-force member. This is because there are forces acting at only 2 points on the bar BE, and a nice slope triangle of 4, 3, and 5. And likewise, I had made a statement here saying that if you have pins B, C, D, and E, there are only 2 members of the frame connected at these pins, so we do not need to draw a pin diagram. But if you have more than 2 members of a frame at a pin, then we need to draw the pin diagram. Or if you have 2 members and an additional external force acting on the pin, you need to still draw the pin free body diagram. Okay, so that's something that you have to do. Once you do this, then it's a question of deciding what to do. I'm starting off the free body diagram of CD. I look at that. Once again, 4 unknowns, but I can find at least 2 of them and find a relationship between the other 2. Then I look at either the free body diagram of FED or ABC. It's your choice. Okay, BE already has done its job. Okay, so that's going to be in as a 2-force member. So I look at the free body diagram of this guy here, FED, and then I draw that out here, and then I find the rest of the unknowns. Okay, and so this is the end of this particular problem. Okay, now my next step is to solve the problem on friction that we had for the practice final exam. Okay, so let me solve that. So problem. In this problem, I have 3 boxes which are placed one on top of the other. So let me draw them out. Okay, so here is box 1. Okay, I'm just going to draw 3 boxes. I'm going to I guess duplicate them and change its style to a different color. Then I have one more box which is placed right below that. Let me change that color. I guess it's not letting me do it. Once in a while this gets stuck, so I'm not sure if this is a problem with my pen or not. I guess I have to see if this is indeed the situation. Okay, So I guess this is completely stuck. So let me do the following. Let me cut back the screen capturing and come back again. Okay, we're back again to where I stopped. I had a small glitch with this particular problem. So I'm going to start off again for this particular problem. Okay, so the basic idea is this. I have three boxes here. So I want to change the color of one of these boxes. That was my intention, to make this a different color. Okay, but it did not let me do it, and so this is what I ended up having. Okay, so here are the three boxes, and I'm going to label them as A, B, and C. Okay, so this is box A, this is box B, and then this is box C. All right. And I have a force that is acting on the box A, which is drawn in the following manner. Okay, so here is the force P that is acting on box A, and I'm given certain distances where this force is from each of these boxes. So let me draw out those distances. Okay, so here is one height, which I'm going to call very soon what the total height is. Then I have another height, which is the height of box B. Okay, and then I have the third height. Rather than do this, I'm going to do the following. Okay, I'm going to actually get rid of this guy. I guess cut that out, and then draw it in the following manner. I'm going to expand this creature. I guess I'm just going to completely cut that out and bring it down here, so that I can draw the height with respect to where the force is acting. So this is another height that I'm interested in. Then I have the third height that I'm interested in, which is this height right here. Okay. All right. First of all, each of the boxes have a height of 0.5 meters. Okay, so that's the first thing I'm going to be drawing. Okay, so each of the boxes have a height of 0.5 meters, and the width of each box is 0.2 meters or 200 millimeters. Okay, so these are the distances that I have. So this is 0.05 meters, 0.05 meters, 0.05 meters, and for this first box A and the box and the force P, this distance is 0.025 meters. Okay, and for the next one, it's going to be 0.05 plus 0.025, which is going to be 0.075. Okay, and this height here is going to be 0.125 meters. Okay, so these are the different heights that I have. I'm going to call this as H1, H2, and H3, if that is okay with you all. Okay, so I'm just going to take this guy and bring it on here, and I'm going to scoot this out a little bit more. Okay, so this is going to be height H1. Okay, this is going to be height H2, and then this is going to be height H3. Okay, and if you want, the total height is 0.125 from the top. From the location of force P to the bottom of the box C. The ground is going to be labeled as D, so I'm just going to have the ground, which is drawn here. Okay, fixed ground. When you do dynamics, you'll see that the ground can also perhaps start moving. You're going to have slip conditions with respect to moving surfaces, with respect to two moving surfaces, and kinetic friction forces, and so on. It's just going to make it more interesting, in my opinion. Okay, so this is location D. All right, and the problem is asking you, okay, and a problem is also telling you that the weight of A is given to you, weight of A, B, and C are given to us. Okay, so the weight of box A is 10 newtons. Then the weight of box B is 30 newtons. And then the weight of box C is 20 newtons. Okay, and we are also told that the coefficient of friction between AB, BC, and CD are given to us. Okay, so given mu AB, this is 0.3, mu BC is 0.4, and then mu CD is going to be 0.2. Okay, this is given to us. Then the width of each of these boxes, they're all the same width. That's also given to us. That's also a crucial information that is given to us. We might perhaps need it. Okay, this is going to be 0.2 meters. Okay, and as usual, we have distances marked in the dotted lines. If I forget, you can always do my job for me. Okay, and once again there was a slight glitch when I started this problem, but that's a good thing that we were able to finish the previous problem, and the glitch is only after we started the next problem. All right. What are the things I need to do? I need to find the minimum force P for motion to impend. Okay, so what do I have to do in this problem is find the minimum force. Find the minimum. I'm sorry. For motion to impend. Okay, this is the thing that we need to do in this particular problem. Okay, and how do we do this? The first thing is you always want to look at the different cases of impending motion, list down all these cases along with the friction equations, and as you know, we will call the friction force as F mu. Between bodies A and B, it will be F mu AB, and so on and so forth, and likewise for the normal forces. Okay, and so I'm going to list the cases of impending motion first. Okay, so the solution is done by the following manner. Okay, so solution. Okay, we shall list cases of impending motion. And then eliminate via a judicious choice. Okay, all right, so here are the cases of impending motion. As I apply the force P, all the boxes can slide as a single unit. Okay, so the first thing is this. Okay, so all the boxes slide together as a unit. What are the equations that are available? I can say that F mu CD. If you take a look at the boxes here, CD is going to have motion that is impending. So F mu CD is equal to mu CD times N CD, but location of NCD is not known. Okay, that is one important thing. Okay, it is actually not known to us. And then the other equations that I have are F mu BC is equal to mu BC, I'm sorry, is less than mu BC times N BC, and then F mu AB is less than mu AB times NAB, and all of these equations have to be satisfied whether they are an equality or an inequality if you assume that the boxes slide together as a unit. Okay, that's the first case of impending motion. The second case of impending motion, you can take a look at the problem. You can say that, okay, as the force P is applied, the boxes A and B move together, the box C is at rest. Okay, so that's my second case. So second case of impending motion. So boxes A and B move as a unit, and C is at rest. Okay, which means that if I write the friction equations now, here is what I end up having. Okay, F mu BC is going to be the impending surface because box B is going to move relative to box C, right? Which means that F mu BC is going to be mu BC times N BC. F mu CD is going to be less than mu CD times N CD. F mu AB is going to be less than mu AB times N AB, and but location of NBC is not known. That is an important thing, as we had seen in the previous case. Okay, so location of NCD was not known in the previous case. Here location of NBC is not known. Then there is a third situation of sliding motion, which is quite obvious to see. I can say that the box A is moving but B and C are at rest. Okay, this is the third case of sliding motion. Okay, I'm just going to call this as case 3. So box A slides, but B and C are at rest, which means that my friction equations are now the following. So F mu AB is going to be mu AB times NAB. F mu BC is going to be less than mu BC times NBC. Okay, and then F mu CD is going to be less than mu CD times NCD, but location of the force NAB is not known. Okay, so when you have sliding motion, the location of the normal force is typically not known at the impending surface, but you have an equality for the friction and the normal forces at the surface where there is impending motion. Now we come to the cases of tipping. So this is the second situation. This is the third situation that we have. Let me change the color of this to, I guess, just to make it stylish. I'm always worried that I might just freeze up again. The other thing I can say is the following. I can say that, okay, A, B and C tip together as a unit, or A and B tip together as a unit, or just box A tips by itself. Okay, these are the other three cases of impending motion which I'm going to write down. Okay, so I have the fourth case where I'm going to say that box A, B and C tip together as a unit. A, B and C tip together as a unit. Okay, and in this situation, here are the equations. You will see that F mu AB is less than mu AB times NAB. F mu BC is less than mu BC times NBC. All of these are remaining inequalities. Less than mu CD times NCD. But location of NCD is known. Okay, this is the key statement. Okay, location of NCD is known, which means look, this is going to be at the cornermost point of contact. Okay, so this is one thing. Then we can say that A and B tip together as a unit and C remains at rest. So this is the next case. A and B tip together as a unit, but C remains at rest. Okay, which means that my equations are going to be the following. I'm just going to copy these equations because the inequalities are going to remain the same. Okay, so with your permission, I'm going to do that. And here is what I'm going to say. Okay, I'm going to copy this statement and I'm going to change a few things. Okay, but in this case, the location of what is known to me? The location of if A and B move together, tip together, then the location of BC is known to me. Okay, so the location of NBC is known to me. Then I come to the last case where the box A tips and then the rest of them remain stationary. Okay, this is the last case. Okay, so box A tips by itself and B and C remain at rest. And when we say that something is tipping, then it means that it is as if it is grabbing a certain point on the box and trying to rotate about that point as a fixed point. Okay, so in this case also I have the following situation. I'm just going to copy this figure. The inequalities remain as they are. Okay, as you know, the thing that changes is the following. Now the location of NAB is known to me. It is going to be at the corner point between A and B, the rightmost corner point. Okay, this is going to be at the rightmost corner point between C and D. So maybe I should make a statement. Okay, this is at the rightmost corner point between C and D, and maybe I'll just copy this and bring it to the rest of them as well. Maybe I can do that. This is at the next situation, the rightmost corner point between B and C. Okay, and then the last one is going to be between A and B. Okay, at the bottom. Okay, so the bottom rightmost corner point between C and D, bottom rightmost corner point between B and C, and then the rightmost corner point between A and B at the bottom. Okay, so these are the three tipping cases of motion that we have. And what we have to do in this problem is we have to first eliminate the cases of tipping, and then we will then say, okay, once I eliminate the cases of tipping, then I'm going to start looking at the cases of sliding. Okay, so the basic strategy is the following. Okay, eliminate the cases of tipping first. Try to eliminate cases of tipping by finding the minimum height at which the boxes are on the verge of tipping and sliding, and on the verge of sliding. Once we do this, and if we are successful, then go to the sliding cases. Okay, then go to the individual sliding cases. Okay, so this is the first thing we got to do. And so to proceed towards that, here is what I'm going to do. I'm going to first assume that A, B, and C tip together and they are on the verge of sliding. Okay, so first thing is to eliminate tipping. This is our key statement here. So try to eliminate the cases of tipping. And to do that, I'm going to start off by saying, okay, so say or assume. Let us assume that A, B, and C are tip and are on the verge of sliding. Okay, we shall find H minimum for this case, which means that I'm going to draw the free body diagram of A, B, and C put together. Okay, so let me do that quickly. Okay, by doing the following. Okay, so let me start off by saying, okay, here is box A, and then box B and box C. Once again, I'm a little worried about copying this and pasting this, so with much trepidation I'm going to do that here. Okay, so then I'm going to just do that here as well. Alright, so I'm so far successful. So this is going to be box A, B, and C, and I'm going to say, okay, here is where the force is acting. So let's say that here is the force acting P. Okay, this height, I don't know this height, but before that I have to draw some forces here. This is the weight of A, then I'm going to have the weight of B acting at the center of mass of B. I'm going to have the weight of C acting at the center of mass of C. So this is going to be WA, this is going to be WB, and WC. Okay, and these distances are known to us. So distance from here on to where the line of action of these different forces, the weights are acting, is known to us as 0.1 meters. Likewise, from here to there is known to me 0.1 meter, and then likewise here as well. I'm not going to do this for the remaining pieces. We're just going to assume it. I'm going to call this contact point here as the point E. Okay, and then I know that because it is on the verge of tipping, the location of the normal force NCD is known to me. So this is going to be NCD. Location of the friction force obviously is going to be in the direction opposite to the direction of impending motion. Okay, so this is F mu CD, and then we say that, okay, F mu CD is equal to mu CD times NCD. This is because it is on the verge of tipping, sliding. Okay, so here is my statement. Of course, I have to draw a minimum height here, so I'm going to call that as H minimum. Okay, so this is a H minimum for case A. Okay, which is where I'm saying all of them are on the verge of tipping and sliding. Okay, and so we're saying that since it's on the verge of tipping, so verge of tipping, which means that location of NCD is known to be at point E, and then verge of sliding we know that in this case F mu CD is equal to pardon me, mu CD times NCD. Okay, and so once we have all of these, then all I have to do is start summing forces in the y direction, summing forces in the x direction, and so on and so forth, and then summing moments about the point E. Okay, one thing I want to do is I want to take a look at the problem that I have. Okay, so for me in this problem I'm just going to copy this and bring this creature down to where I have the free body diagram drawn. Okay, so I'm just going to copy that, and I guess my situation is I'm going to move this a little more. So I moved it here. Okay, and my hope is I can show you this free body diagram as well. Okay, and we can see that of course I want to maybe bring it here. Okay, and we can see that I just want to make a note here. So note H given for this case is H3 is equal to 0.125. Sorry. As you can see, that is that creature there. So my aim is to compare H minimum A and H3. Okay, so the aim here is to compare H minimum A and H3. If H minimum A is greater than H3, then tipping is not going to take place. If H minimum A is less than H3, then we are on our way to finishing the problem much more quickly. Fortunately or unfortunately, that might not be the case. Okay, so I'm just going to look at the free body diagram of these three boxes and some forces. I'm going to let you figure the forces and so on. So forces in the y direction, NCD is equal to WA plus WB plus WC, which means that NCD is going to be 60 newtons. I'm going to sum forces in the x direction, and I'm going to get obviously F mu CD is equal to the force applied P. Then from verge of sliding we have F mu CD is equal to mu CD times NCD. Mu CD is known to us, at the beginning of the problem. You were told that mu CD was 0.2, so this is 0.2 times 60, so which means that this is 12 newtons, which means that the force P is equal to 12 newtons. Okay, which is obtained from here. Okay, substitute from there. All right, then what I have to do is, since it's on the verge of tipping, I can sum moments about the point E. Okay, so verge of tipping which means that sum of moments at the point E is equal to 0. If I look at the point E, here are the moments WA, WB, WC, distance of 0.1 meters, and then P times H minimum A. Okay, these are all balanced together, so I end up getting the following. So P times minimum A is equal to WA plus WB plus WC times a distance of 0.1. Solve for H minimum A, and you'll end up seeing that this is approximately equal to 0.5 meters. Okay, so this is WA, WB, WC, so this is 60 times 0.1 divided by 12, or 0.5 meters, which means that H minimum A is 0.5 meters. H given, which is equal to H3, is 0.125 meters, which means that H minimum A is greater than H3, which means that we can discard the case of A, B, and C tipping as a unit. Okay, which means that we have discarded this particular case. All right, so this is a good start, which means that essentially I can go back and say that okay, case 4 is not going to work for me. Okay, so because of the fact that H minimum A greater than H3, so we can discard case 4. But I still have 2 other cases to contend with, so I'm going to go and look at the next case where I say, okay, let me assume that A and B tip together, but they're also on the verge of sliding. Let me find a minimum height and do the same thing. Okay, so the next situation is the following. So let us assume now, let us assume A and B tip together as a unit. And are also on the verge of sliding. Okay, like we did in the previous case. Okay, we are going to say, okay, then we will find the H minimum for this case. Okay, this is the next step for us. Okay, we shall find the H minimum for this case. Okay. And I'm starting off with the free body diagram of A and B together as a unit. Okay, so I'm just going to copy some of these figures and get rid of them. I just want just the 2 of them. Okay, I'm just going to copy that and bring it down here. Let me see how good that looks. All right, so this is not too bad. Okay, so here is I guess I can get rid of these 2 guys. So I'm going to cut that off and cut that off. And so here I have the force P once again, which is acting. Okay, and now I'm going to have I'm going to call this point as the point G. Okay, this is because I know the location of where the normal force is going to be acting for this bar here. So this I'm going to call as NBC, and then this is F mu BC. Okay, and I know that F mu BC is mu BC times N BC because it's on the verge of sliding. And then I'm going to call this height as H minimum for case B. Okay, which is the situation that I'm considering. So H minimum for B. And what is my aim? My aim is to do the following. I'm going to take a figure from before WA and WB. The weight of WA is known. The weight of WB is also known to me. I'm going to copy this figure from above here. Okay. And I'm going to say the following. Okay, so if I copy that and bring that down here, okay, so here is the situation that I have given in the problem. Okay, okay, and my aim is the following. Okay, so aim. Okay, so compare H minimum B with H2, which is equal to 0.075 meters. Okay, that is this height here. Okay, and we are on the verge of tipping and we are on the verge of sliding. So if I do that, so verge of sliding, which means that F mu BC is equal to mu BC times NBC. We are on the verge of tipping as well. Then we see that okay, location of NBC is known to be at point G, and all we have to do is go on our merry way and find out what these values are. Okay, so let's do that. Okay, so I just start summing forces in the x direction, and I end up getting P is equal to F mu BC. Then I start summing forces in the y direction, Okay, I end up getting NBC is equal to WB plus WA, which means that NBC is equal to 40 newtons, right? 30 plus 10, 40 newtons. Then verge of sliding implies that F mu BC is mu BC times NBC. So this is going to be 0.4 times 40 or 16 newtons, which implies that P is equal to 16 newtons. Okay, that is coming from here. Then verge of tipping, which means that I can sum moments about the point G, verge of tipping, which means that sum of moments at the point G is 0. This point is going to act like a fixed point for this body. Okay, if I do that, then I see WA WB times 0.1 balanced by P times H minimum B, right? So I can say the following. So H minimum B times P is equal to WA plus WB times 0.1, or H minimum B is equal to 40 times 0.1 divided by 16, and this is approximately 0.25 meters. Okay, so which tells me that H minimum B is 0.25 meters for A and B to tip together as a unit, but I see from the figure that H2 is 0.075 for the location of the force P based on information given to me. So I see that but H2 is 0.075 meters, which implies that H minimum B is greater than H2, which means that boxes A and B do not tip together as a unit, which means that we can discard case 5. Okay, and I want to go ahead and make a statement for case 5 right above here, okay, where we had case 5, and so we see that in this case H minimum B was 0.25 meters and H2 was 0.075 meters. So H minimum B greater than H2, which means we can discard case 5. Okay, it's a pretty tedious problem, as you can imagine. Okay, so my next step is I have to take case 6 and then look at case 6 and then see, okay, can I discard case 6 as well. Okay, so that's my next step. I go back to the drawing board. Okay, so let us assume now, so I'm going to say this is C. Let us assume A tips by itself and B and C are at rest, and that A is on the verge of sliding, okay, relative to B and C. Okay, same idea. I have to figure out and see, okay, if this case can be discarded or not. We shall find the minimum height for this case as well. Okay, so we shall find minimum C for this case. Okay, so I'm going to draw the free body diagram once again from before. I'm just going to copy this figure here. Okay, just going to copy that and bring that down here. Okay, and probably duplicate one of these guys so as to complete the figure, and this guy has to, I guess, come down here. I'm going to call this height as H minimum C. Then I'm going to call this contact point. I guess let me first draw the forces at this contact point because it's on the verge of tipping and sliding, right? So this is going to be NAB, and then this is going to be F mu AB, which is equal to mu AB times NAB. Okay, and I have this contact point, which I will label as the point J. Okay, because I'm almost running out of alphabetical letters here. I have to start using probably a different language. All right, and then for comparison, I'm going to bring in our figure from before. Okay, which I'm going to copy from here. This is my figure from before. So copy that and bring that creature down here and show it in tandem with this figure here. Maybe I can get rid of that guy. Okay, and I want to scoot this down a little bit. If you don't mind. Okay, and our aim here is the following. Okay, so aim here is to compare H minimum C with H1, 0.025 meters, and H1 is this height that you can see here. Okay, and we say that it's on the verge of tipping, so contact point is J, location of NAB is known to us in this case. Okay, so verge of tipping, which means location of NAB is known, and then it's also on the verge of sliding. Which means that F mu AB is mu AB times NAB. Okay. All right, and then sum of forces, sum of moments, and sum of forces in X and Y. That's about the end of the story here. So if I sum forces in the X direction and set that equal to 0, you will find out that P is equal to F mu AB. This is a no-brainer. Okay, sum of forces in the Y direction is equal to 0. You see the same theme being played out again and again throughout the semester. Sum of forces, sum of moments, and then that's about the end of it. Okay, so if I see that this is NAB is equal to WA, which is equal to 10 newtons. Okay, then verge of sliding, I have F mu AB is mu AB times NAB, right? This is on the verge of sliding, which is equal to 0.3 times 10, or 3 newtons, which implies that P is equal to 3 newtons. Then I sum moments about the contact point, which I had labeled as J. Okay, then verge of tipping. Okay, I sum moments about the point J, WA times 0.1 balanced by P times H minimum. You can do the moments counterclockwise, clockwise, and all that. Okay, so sum of moments at J is equal to 0. If I do that, I end up getting H minimum C is WA times 0.1 divided by P, which is equal to 0.33 meters. Okay, so H minimum C is 0.33 meters. H1, which is given to us in the problem, was 0.025 meters, and so H minimum C is greater than H1, which implies that this case can be discarded. Okay, so box A cannot tip, which means that we can discard case 6. Okay, so I can go back to the problem and then write this down as well. Whenever I see case 6, we can write out that H minimum is 0.33 meters and H1 was 0.025 meters, and so can discard case 6. Okay, and so the basic idea now is I'm done with all the cases of tipping. So all the cases of tipping have been discarded. So that's a basic summary that I have from what we've done so far. So which means that we can now neglect all cases of tipping. Okay, which means that we now have to select, which means we select the case of sliding and then test the equations. Okay, so this is the situation that we will have to do. Now here you have to be a little careful and maybe a little smart. What I find out is, if I looked at just the box P, just the box A tipping, I had a force of 3 newtons. If I looked at box A and B tipping and sliding together, 16 newtons. Box A, B and C sliding together and tipping, it's 12 newtons. So I'm going to assume that box A is the one which is on the verge of sliding, and I'm going to prove that the equations are satisfied, because that gives me, when I consider the case of tipping and sliding together, that gives me the lowest force. Okay, so what I'm going to do is the following. I'm going to assume. So let us now assume case 3. That is box A slides and B and C at rest, which means that here are my equations. Okay, I'm just going to bring them from where I had written them down previously. Okay, so this is the set of equations that I had from before for case 3. I'm going to copy these and bring them down here. Sorry for going up and down. I hope you're not getting your head spun around. Okay. All right, so this is the situation. So I'm going to draw the free body diagram for A and then B and then C. Okay. All right, or A, B, C, and then C, if necessary. Okay, so I'm going to draw the free body diagram of A. Okay, and if I do that, then here is the situation. And I start looking at the different forces that are acting. So first of all, there is the weight of the body A, which is given to me. Then the normal force which is acting, I don't know the location here, so I'm just going to draw it at an arbitrary position. So this is NAB, and then this is of course F mu AB. Okay, this has to be a straight line. This is F mu AB, which is equal to mu AB times NAB, and then I have the force P that is acting on this box. Okay, and then I have the height, which is now known to me. Okay, this height is known to me to be 0.025 meters. Okay, and here is what I'm going to start by summing forces in the x direction and y direction, which means that the force P is equal to F mu AB. Then I sum forces in the y direction and set them equal to 0. I get NAB is equal to WA, which is equal to 10 newtons, which means that P is equal to F mu AB is mu AB times NAB, or the force P is equal to 0.3 times 10, or 3 newtons. But we need to start checking the other two equations of friction. So my aim now is to check these two equations. So I'm going to copy that and bring that down here. Okay, so my aim now, let me scoot this a little to the side. Okay, and so the aim to test and see if these two equations are valid if we choose case 3. Okay, and towards that, there are several ways you can do this problem. I'm going to draw a free body diagram of B and C together, and then free body diagram of just the block B by block C by itself. Okay, so here is my situation. Okay, so look at B and C together, and then block B by itself. Okay, so free body diagram of B and C together. If I draw that out here, that's what I'm going to get. Okay, so one here, and then this is B and C together. Okay, of course they're the same height, but you might not recognize it by looking at this figure. I'm just going to scoot that up here. Okay, and then I have the forces acting. So there is the weight of box B, and then there is the weight of box C. That's not a circle, that's a straight line. Weight of C, there is no force here. The force F mu AB, if you see, F mu AB is pointing to the left on box A and in B interface, so it's going to be pointing to the right here. Okay, so this is going to be pointing to the right. So this is F mu AB, which I know to be equal to 3 newtons from above. Okay, and now I have NCD, which is acting vertically up, and then I have F mu CD, which is less than mu CD times NCD. We need to check and see. Okay, and from here I can say that, okay, sum of forces in x direction gives me F mu CD is equal to F mu AB is equal to 3 newtons. Sum of forces in the y direction tells me that NCD is equal to WA plus WB plus WC, I'm sorry, WB plus WC, and I have an extra force that I need to account for in this case, which is the normal force, which is coming from the box B and A. So this is NAB, so this is WB plus WC plus NAB, and NAB was equal to I think 30 newtons from above. Okay, so there was equal to 10 newtons from above. Okay, so which means that for me NCD was equal to a total of 60 newtons. Okay, and then now I have to test and see. Okay, F mu CD max, which is equal to mu CD times NCD, is going to be the following: 0.2 times 60, which is equal to 12 newtons. But F mu CD from calculations is equal to 3 newtons is less than mu CD times NCD. Okay, which means that we know F mu CD is less than mu CD times NCD. So one of the inequalities has been satisfied. So we have satisfied this creature. We need to satisfy the next one. So I'm going to look at the free body diagram of just the box B by itself. Okay, to satisfy the next inequality, to see if F mu BC is less than mu BC times NBC, look at free body diagram of B. Many ways to do this problem. This is just one particular way. Okay, so I'm going to draw the free body diagram of B. I have a couple of things going on in this free body diagram. Okay, first of all, the different forces that are acting, the weight of the box, that's the first thing you got to draw. Okay, so this is weight of B. Then I have the normal force from AB, then I have the normal force from BC, which I don't know. Then I have the friction force F mu BC. Then on this top box I have the friction force F mu AB, equal and opposite to what I had on box A. This was known to me as 3 newtons. This was known to me as AB was 10 newtons. The weight of B was given to me as I think 30 newtons. Now F mu BC, we need to check and see if this is less than mu BC times NBC. Is that right? Okay, we sum forces, which tells me that F mu BC is equal to F mu AB, which is equal to 3 newtons. Then I sum forces in the y direction. I get NBC is equal to NAB plus WB, which is 30 plus 10 or 40 newtons. Then I find out F mu BC max, which is mu BC times NBC. Okay, what is this going to be? We had mu BC from before. If I go back and look at the value of the friction force, this was 0.4, right? So that is 0.4 times 40. So this is 16 newtons, which obviously means that F mu BC, which is equal to 3 newtons, is less than mu BC times NBC, and so F mu BC is less than mu BC times NBC. So that inequality is also satisfied, which means that we chose our case very judiciously, and we can obviously see that since this inequality is also satisfied, that is also satisfied, the minimum value of the force P is going to be 3 newtons, and case 3 is the winner here. Okay, so which means that since all the friction equations are satisfied for this case, are satisfied for case 3, this is the winner, which means that P minimum is equal to 3 newtons to cause motion to impend, and at this point the box A will start to slide, and as soon as the force P minimum goes beyond 3 newtons, then if it becomes 3.1, then the box A is going to start having an acceleration, and then you can apply Newton's laws and say, okay, F is equal to m times A, and if you know the mass of box A, you can find the acceleration of box A. All right, so that's about the problems that I wanted to solve. But a couple of quick words, I don't want to write them out, I just want to say them out here. In general, strategy for the final exam is, first thing is, to stay calm. Okay, so stay calm. Okay, then start with the problem that you're most comfortable with. Okay, start with the problem you are most comfortable. Okay, this typically for me, this is like a moment of inertia problem, because that is just geometry. There is nothing in those problems. Those are just garbage problems, but they're of course very important when you're doing mechanics of materials, as you will see when you look at states of stresses and so on. Moments of inertia are very important for us in terms of knowing the distribution of the stress straits. That's something that I do, and then I typically allot like around 20 minutes per problem. Okay, so allot about 20 minutes per problem. Okay, and then the basic idea is, if you go past the 20 minutes, then move on to the next problem. Okay, so if you go past 20 minutes, move on to next problem, and then come back to problem where you left off. Come back to and if it were me, this is the order that I would solve the problems in. If I wrote the exam, I would solve in the following order. I would do centroid, moment of inertia problems first. Okay, then I would look at trusses. Trusses are my favorite problems. This is the reason why I became an engineer, as I told you in lecture a long time back. Okay, it still makes me very emotional to talk about trusses. Then I would look at frames, and then I would finally look at friction is always tricky. Okay, trusses are straightforward. Frames can be tricky. but they're typically just drawing free body diagrams and so on, so I don't see any issue in you solving a problem on frames. You just have to see, okay, hey, I have only 3 equations of equilibrium, but if I have different rigid bodies, I can use 3 equations for each rigid body. So if I have a total of 6 unknowns, and if I have 2 rigid bodies, then I have 3 equations from each rigid body. So 6 equations in total, 6 unknowns in total, and I can solve for them. Of course, the solution may not be just straightforward, but you can still solve for them using substitution or something. So that's my basic attitude for these problems. And I wish you the best of luck. Okay, so wish you the best of luck. And you are the best. I take great pride and privilege in teaching at Ohio State. For me, this was a dream come true when I started doing my teaching, when I started my teaching career at Ohio State. So I'm proud to see students like you take my course, become good people, good human beings, become great engineers, and continue this tradition of going forward and paying it back. Okay, take care of yourselves. I hope you're all staying happy and healthy. Wish you the best. If you have any questions, please feel free to email me or talk to me before the exam. Okay, take care of yourselves. Bye bye.